Alrighty, we are now live on the air. This is Dr. Daniel Karras for Talk Live on Cyborg Alpha TV. That's right. And I've titled it Beta. The reason why I titled it the Beta, we're still going to be talking about atheism and the atomic bomb. That's going to be our topic for the next almost 12 weeks. When we come back, starting on August 11th, for the next 12 weeks, for about 12 weeks, we'll be talking about this topic. We're going to go further into depth into this. And but I put the title Bait up there because tonight is our last broadcast in the test series. This series of broadcasts were done specifically for those who wanted to. This broadcast was done sort of test out what can be done on Google Plus Live. Does it work? How does it work? What are the options? I'm on Linux, so that in many cases there's a lot of unknowns to what's going on, and so this was my test period, we'll call my initial test period. So, and tonight is our last broadcasts. From here, of the test period. So the test period ends tonight. We will be on a hiatus. We'll be on a break until August 11th. We won't be coming back live until August 11th. And then from August 11th, we're going to go all the way through until probably next year. So we'll see what happens in terms of we'll schedule the breaks out then. But right now, anyways, let's get our day started. I'm going to give you the schedule. Basically, it's the whole program is about 3 hours in length. We do the first hour here. Second hour, basically from 11 to 12, we go to a platform called YouNow. And the last hour, from midnight till about 1 o'clock in the morning, we're at Twitcasting. Twitcasting allows, in terms of my experience, Twitcasting allows for the best interactive experience that I've seen so far. Right now, my most interactive experience in terms of communicating with the audience has been on Twitcasting. That's the most flexible platform. So that's what's going to happen, is that I'm going to leave the Q&A until the Twitcasting platform. So you do have Q&A if you want to hold it off to then. Otherwise, put it in the comments down below. Leave it in the comments down below and go from there. And what I'll do is I always answer the comments, not in the comments down below, but I answer the comments in the video. So, and I give you the credit that, I say who left the question, I say or the comment, and I read the comment out loud as best as I can. Sometimes, if I'm a little fatigued, then the reading isn't so good, and it's always a bit of a rough start when you're doing live, because you got to get yourself in the right mood, you got to get yourself in the right frame of mind, and the more fatigued you are, the worse it becomes. So, so let me see here. Yeah, so here it is. I'm gonna post in the chat here where we're going at 11 o'clock. So at 11 o'clock, we're going to YouNow, and there's the link for that. And at 11 o'clock, then at 12 a.m. we're going over to Twitcasting, and that's going to be your Q&A. So the Q&A will be in Twitcasting. We can have a discussion as well. So basically, you're in a miniature form, a miniature conference, if you will, and at basically at midnight on the Twitcasting platform, this is where we have our discussion. This is where we have people talking back and forth. They ask questions, and you go from there. So let's get on to our topic tonight. We'll welcome anyone who comes in late. I'm not going to be able to see who comes in or who doesn't come in because I'm moving over to my notes now. As I said before, the way the Talk Live is changing is I've rolled Talk Live into Insta vlogs, And these are the live essays based on notes inside of InstaVlogs. InstaVlogs was set up to hold my research notes, because CyborgAlphaTV is, in many cases, it's all the behind-the-scenes work of my research. So you're seeing all the rough cuts. You're seeing all the mistakes. It's the research live as it's going on. So there's a lot of mistakes. There's a lot of rough edges to it, because you're seeing things unpolished. You're seeing my notebook. You're seeing my journals, and none of these things are really gonna be polished and sort of how should I say? They're not going to be in the final presentation stage. So InstaVlogs begins with my ad hoc notes, and taking my ad hoc notes and organizing them into more organization, bringing them more together. So the creation of the notebook, and then based on the notebook, the new thing now, these TalkLive are essays taken from the notes, but the essays aren't written prior. I'm doing the essay as we're speaking. This is the essay as we're coming as we are going along. So this is kind of what you're seeing here. Is you're seeing an essay constructed live on air, and that's primarily what a lecture is too. A lecture is basically an essay, and although many people write their essays ahead of time, I decided that because this is part of the process moving to documentaries, that the essay will be a good part, and it's good practice for me, particularly when I want to do my documentaries, to start speaking like this. Because what happens is that there are so many different tangents and things you can think of as you're going through these topics. It's hard to script things. It's very difficult for me to script things, because there are always better ways of phrasing things. There's always different things you want to bring in, some things maybe you want to leave out, and you never know exactly to the last minute what you want to do. So in many cases, I go in with a set of notes, and then I let the rest happen as the talk unfolds. So the talk becomes the first essay. It also becomes the to some degree, it will become the basis of the first cut, the rough draft of a documentary that will sort of come later on. And then, of course, as a doc zone is set up, that means the doc zone will have finished or final cut documentaries in there, and that's what you're going to see on Physics TV. Physics TV is going to be the polished, finished product, and so you can always look at Physics TV, watch Physics TV, want to see what's going on, how did the product get put together. You can always go back to CyborgAlphaTV and sort of see what's going on there, what all the behind-the-scenes stuff was about. You know, what went on, what happened, how did I get to where I am now, or you know, different things like that. In other words, CyborgAlphaTV is always going to be behind the scenes. It's not going to be seen. It's going to be a sort of something that's hidden. As for where we're going today, we're going to sort of finish up the whole thing on how atheism and the atomic bomb evolved from the test topic of atheism and Tesla. And it's all part of the question that revolved, as I was doing my research, is atheism dead? One of the problems in physics, as physics develops, and you start doing research in physics, more often than not, you're talking about the structure of the universe, you're talking about the creation of the universe, you go back and talk about the Big Bang Theory, and you're looking at evidence of this. And as you're talking and looking at the evidence for this, the presentation of research is not, for a researcher, is not presented in the same way it's presented to the public. There is one view for the public and another view for researchers. And this is actually how, if you're talking about this, if you talk about Tesla and stuff like that, you can talk. People say, "Oh, you're gonna get into all the conspiracy theories." And well, yeah, you do. You do have to touch on the conspiracy theories. But the thing is, if you're a researcher, you're doing physics, then you know Tesla not from the conspiracy theories, but you know Tesla from the from the research side of things, because Tesla was a scientist, and so that's how you know Tesla. But you also know that because if you're working on the area of atomic and nuclear physics, and that's one of the areas I do work on. I'm working on quantum mechanics. I'm working on superstring theory. I'm working on a lot of these other different theories, sort of push things forward, because physics is kind of in a state right now where things have kind of fallen apart. And the next direction is sort of anyone's guess. We're kind of back in the wilderness once again. And it's as we end up back in this wilderness of physics that the previous view of physics, and particularly the world itself, as being finite and determined, that's what we call deterministic. And that means that things are known. When you write down an equation, it's not simply an approximate model, it's a law. And that's why you have Newton's laws, you have the laws of thermodynamics, you have Kirchhoff's law, you have a lot of different laws in the older physics. In the newer physics, I'm talking about the current physics, and particularly in the areas of quantum mechanics, atomic physics, and this area as such. What you end up having is you end up having to deal with equations that are not exact, but rather approximates, and that the equation always has to be adjusted. And this is sort of status quo. The equation has to be adjusted to fit the data. And now, normally, if you go back to your standard deterministic physics and say this is the law, I mean, this was using religious terms here. Adjusting your equations, adjusting your theory to fit data was absolute heresy. I mean, because if your theory was absolute truth, it was scientific truth, then to adjust the equation to meet the data, well, now you're contradicting your absolute truth, and you no longer have absolute truth, but you have now a theory and understanding, not the understanding, but an understanding. If you're a physicist where I'm at right now, and you're doing the work in the quantum mechanics, you're doing the work in quantum physics, and you understand that the universe is now, this whole universe, particularly the atomic and subatomic universe, is probabilistic, then you understand, in many cases, speak in probabilistic terms. In other words, when you say you know something, you're not saying it in the absolute sense. You're saying it in the relative sense, that you have an understanding, you have some knowledge of what you're looking at or what you've experienced, but there is a total knowledge, or an experience called the absolute knowledge, the truth, that fundamentally eludes you. In other words, you can never achieve it. You can only approach it, but you can never achieve it. And this is where you bring in calculus. And as you talk about calculus, you get into limits. Limits are how you deal with asymptotic curves. An asymptotic curve is a line that approaches a particular point on a graph. Let's say it's an X point. Let's take this screwdriver here. We go along. Our X-axis is horizontal. At some point in time along X, there is a line that goes vertical. That the graph goes up, 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 up. And why it's going up? Because it never actually reaches this point on X. It never actually here's your origin. Here's the origin. You go to you get to this point here. There's a point on the graph, but you never reach the point. You just get close to it. The way, and then what happens is the curve doesn't look flat and then like that. What it does, it has a little. There's flat, and then there's a little curve down here near the corner when you have the corner here between the two lines. When you have the corner between the two lines like this, right in the lower left-hand corner, there's a little curve there, and then the line goes sort of up straight. Not an actual straight line, because it is tending closer and closer to the point X. on the line. But because that point x is undefined or infinite, in other words, it's asymptotic, you can never reach it. You never actually touch that line. You can approach it, you can get close to it, and this is what they talk about. The mathematical term in calculus, in the limit, is how close do you have to be to state that you are now fundamentally there. Now, this is you have to remain keep this sort of understanding. To say you're fundamentally there, you still have the understanding that you are not there. You just simply say you're close enough that, you know, at this point in time, or for what we're looking at, that the rest doesn't simply matter. And it doesn't matter, again, it's not an absolute that it doesn't matter. It's just at this particular point in time, what you're looking at for that type of thing, it doesn't matter. And this is sort of what happens with the Higgs boson. There were certain amounts of data that had to be, there's certain amounts of the equation that had to be sort of taken away and sort of not looked at in order to get the Higgs boson, because they were looking at in many cases, different parameters. And in the parameters they were looking at for the Higgs boson, the other parameters were not considered to be as important. So as they did that and adjusted the equation for the Higgs boson, and that's what they did. They the Higgs boson, the data for the Higgs boson did not meet their expected equation. They had to adjust the equation to the Higgs boson. And so you had a very loose fit for the equation. And then afterwards, they went in and started tailoring the equation to the Higgs boson. Now, the theorists who basically are at CERN, this is the European body, and the Europeans are typically theorists. They operate on theory. They do experiments to prove theory. They don't do experiments for exploration, but they do it to prove theory. Came out and said that they found the Higgs boson. Where if you listen to the actual research that comes out, that's the actual research, and they're done. The research reports are given at colloquiums, or sort of colloquia. Colloquia are lectures given by various different researchers on various different research topics at a variety of different universities. Most universities have some, particularly at the research centers, they have their colloquia, where they have visiting professors who will come around and talk about their research. And this was done for the Higgs boson. If you go to a colloquia, and in the audience are other physicists, so he's not speaking to a general audience. He's speaking to other researchers. He's speaking to other physicists. The terms they use and the information they bring out are completely different from what you see on the news reports. And this is what you're going to be, if you're talking about, these health reports that are in the newspaper about what's bad, what's good for you, and what's bad for you. You got to be very careful, because what's in the paper is not what, and what's in the news, mainstream news, is not what is in the research papers. They're not two totally different things, and they're not even comparable. In many ways, they're not even comparable. And so what happens is the Higgs boson. If you understand physics, you go back into the history of physics, particularly atomic physics, you'll see that there is a large degree of unknown and uncertainty within physics. So if this is the case, if uncertainty and unknown, and this is actually where you have the Heisenberg uncertainty principle, if this is your standard now, the uncertainty is your standard, the Heisenberg uncertainty principle becomes your base understanding, then the entire concept, or should I say the initial statement of scientific truth disappears. Because you can't have scientific truth if you are uncertain about things. And so when you go back and say, well, this is simply for atomic physics, right? It's down on the molecular level. It doesn't really affect us. Okay. Until they start bringing the data that they had from the Hubble Space Telescope and the new larger telescopes from the 1990s on, they began working on the models with the new computers and the supercomputers. They began working on models of the universe. How is a galaxy held together? What's the model of the galaxy? What's the model of, what when you see what's going on in the universe? How do you get from the Big Bang, what they talk about the Big Bang, and these are all equations. This is all calculus. How do you get from the Big Bang to the structure you see now? And as they start adding in structure, they start adding in what they saw from the Hubble Space Telescope. The equations didn't work. The equations they had for the structure of the universe didn't work. So they had to go back in, and they had to fudge things again and again and again. They kept adjusting and kept adjusting and adjusting. They finally said, well, let's take the assumption here. But the way they do their calculations, they look at fundamentals. What do you fundamentally have in the universe? You have energy and you have matter. We know this from equals mc squared. That's Einstein's equation. And that gives you a relationship. You know that every time you have matter, you have energy, and that there's a direct relationship with matter and energy. And this is why you have, in sort of called classical physics, you have the conservation of energy and conservation of mass. And the reason why they go together, the conservation of energy and conservation of mass, has to do with Einstein's equations, E equals mc squared. That's the relationship. And E equals mc squared is not simply a formula in terms of a numerical formula. It's a model. It's an understanding of the universe that you have. Whenever you have energy, you have mass. Whenever you have mass or matter, you have energy. And that's the relationship between the two. And that's what E equals mc squared actually describes. That's the mathematical description of this. It's the model. But the standard understanding didn't seem to fit with what they were seeing in their models. So they said, okay, let's add in this imaginary energy and imaginary matter, right? Because anytime you add in energy to an equation, you have to put in a corresponding amount of matter, amount of mass. And because it was unseen and imaginary, they termed it dark energy and dark mass, and dark matter. And it could also be dark mass as well. But these points we'll get into later on. We'll get into some of the more finer details later on, rather than right now. But so they started adding in the dark energy and dark matter, and as they started adding in the dark energy and dark matter, the equations started to work. When they start adding it, they added it to the point where they were happy with the equation, we're producing in the computers. In other words, you could see a particular model coming out of a computer. You could see the structure of a galaxy. You could see these different things going on there. And they actually they went back to sort of calculate how much dark matter and dark energy has to be there before you get these equations to work, as compared to what you actually see. Well, it turned out that 95% of the equation, 95% of your model, is dark energy and dark matter. In other words, 95% of the universe is unseen. The part that we do understand is if we can understand that when we look at the telescope, we see from the beginning of the universe to the end of the universe, and we're not doing this. We're not seeing when we look at the telescope the beginning of the universe or the ending or the end of the universe. We have no idea where we are in the universe. We know we're in it, but we don't know we're in the middle. We don't know if we're at the end. We don't know exactly where we are in it, because we have no defined edges to our universe yet. But let's assume that we do have this defined edge. We get to this defined edge. Once we achieve this defined edge, that's only 5%. In other words, our absolute certainty that we can ever approach, once we have the understanding and have been able to see all of the visible universe, we're only seeing 5%. That leaves a 95% level of uncertainty. And understanding this completely wipes out the whole issue of scientific truth. Because you now see this whole uncertainty thing not only on the microscopic level, called atomic physics and particle physics, but you're now seeing the same uncertainty at a huge scale on the macroscopic universe, on macroscopic physics. So on all levels of physics, you're seeing this uncertainty. Let's bring it down in size, right? to demonstrate this uncertainty. The engineers at Boeing thought that they had the latest, greatest computers, and IBM had built them an amazing supercomputer. It was the fastest thing out there, and this was this is around 2000, and they were at a point where they were convinced that they could build an entire aircraft, do all the flight testing with simulators and so on and so forth, and produce the aircraft right out of the simulator, right out of the computer, do the whole design, all the engineering inside the computer, and then go from the computer, build, and then fly it. That's what they did. That's the Boeing Dreamliner 777. Have you been watching the news of the problems they've been having with the Boeing 777? Why? Because they realized when they got to the end, they started flight testing this. You know, they have to go through flight testing that's mandatory, that's regulated by the FAA. And so they did the regulatory flight testing. They didn't do the flight testing to test the different parts. They did the flight testing simply to do to meet the regulations. And they were saying they were convinced that the model was so good inside the computer that they knew enough of what was going on inside the computer in terms of their mathematics, their engineering. That was good enough that they didn't need the flight testing. They could just simply go into production. Didn't work out that way. Didn't work out that way at all. And that was the collapse of the latest model inside the computers. They realized the computers were not smart enough. They couldn't figure out what was actually missing. And what happens is in the 2000s, up to the 2000s, up to the end of the millennium, people were saying we're going to go further and further and try to build everything in the computer, do a lot of testing in the computer. After 2000, they went back to actually doing physical mock-up models again. They started doing the old school testing again because they realized that the model simply didn't have the information and the capacity to do the modeling that was needed. All you could achieve inside a computer with your equations are approximates. You cannot ever achieve the real thing. And this demonstrates the Heisenberg uncertainty principle. So now you have the Heisenberg uncertainty principle at the microscopic level, the atomic level. You have it at the macroscopic level in terms of what holds the galaxy together, in terms of how gravity works and so on and so forth. And now you have it in between, even on the engineering level. So we are now in a physics that is undeterministic. It's probabilistic, it's not absolute, and scientific truth is now gone. There is no more scientific truth. And this sort of what brings us to this whole question. And again, the whole question of anything has, at this point in time, we've not talked at all about religion. And in many cases here, for the beginning of what we're talking about here, for the next 12 weeks, once we start, we're not going to touch on religion at all. We're going to talk briefly about it, but it's going to be adjacent to the subject. The topic is in physics. This whole issue of atheism has to do with what's going on in physics. It has nothing to do with religion. It's not a religious question. This is a question of science. If atheism is as it states, it's a science, then this is a question about science, and it's a major problem now in physics because you don't have the absolute truth anymore. This means the fundamental truth of atheism, the base of atheism, the scientific truth, because that's not there anymore. The scientific basis for atheism is no longer there. But the thing is that, and this is where I bring Tesla into this, because a lot of people can relate to Tesla, both the public side and the research side. And the reason why you have a lot of conspiracy theory surrounding Tesla has to do with the fact that at the time Tesla was doing his work, the industrial complex, the military-industrial complex, was just beginning. This is when the military and the scientists started working together. This is when you had a lot of top secret research being done. We were getting into the early stages of World War II, and a lot of stuff was going on secret in the background. This included a large chunk of the atomic research. And this is why a lot of the atomic research really didn't have an impact until 1945, until the atomic bomb went off. No one really knew what was going on. But when the atomic bomb went off, most philosophers began to realize that their whole concept of philosophy, the modern concept of philosophy, which was prior to 1945, was wrong. In other words, modern philosophy ended in 1945 with the atomic bomb. I would say it was blown up by the atomic bomb. And after 1945, you had the beginning of the postmodernist period. And the postmodernist period was a complete deconstruction of the previous philosophical models. And there was two groups. There was the ones who destroyed and created chaos, and there were those who lived in chaos. In other words, they had no reality. They were based totally in concept. The ones who were conceptual, that life is a concept, that the world is a concept, that the universe is nothing more than a concept. In other words, the reality was no more. Those were the nihilists. On the other side, you had the pragmatists or the realists. The realists were the ones who were they were the modern philosophers, and the pragmatists, the modern philosophers, didn't give up. They kept trying to revive their ideas. But what happens is that out of the pragmatists, as the pragmatists collapsed, as they began to realize their ideas didn't work, they became deconstructionists. They became destroyers, and that's the origin of anarchy. The anarchists are your destroyers. They're socialists. They're like the nihilists. They believe in chaos. They believe in concept. But in this case, the anarchists believe that in order to recreate a more perfect society, to recreate utopia, you have to destroy the society first. You have to burn it down and then reconstruct it again. And this is actually what's been going on since 1945. You've had a repeated burning down of society, a destruction of society, and a rebuilding again to try to achieve this perfect socialist utopia. And it's never worked. It's never really worked because, and I'll show you why with the atomic bomb, it just doesn't work. And this is the whole thing. Is the fact is you can never get to an absolute truth, and because you can't get to an absolute truth on your own, in terms of science, then you're not. There is no end to what you're. There is no perfect utopian society. And so what happens is that the whole understanding of where we go from here in terms of physics, and we're talking about physics here, and how physics impacts or doesn't impact the society. Right now, because there are secret programs, and there are a lot of these special access programs, or the black budget programs. This is areas like Area 51. Area 51 was an atomic testing site. Anyone who does atomic physics, anyone who does quantum physics, anyone who works on superstring theory knows that as part of history, Area 51 was an atomic testing site. And the thing is that this is where I'm going to go in and give you a list of things. And this is the difference between textbook learning and sitting down and actually doing the research. Most people really don't have an understanding when Watson and Crick actually found the DNA molecule. They don't know how they did it, but they just know that they did it. Now, it's actually telling that that this work was done in 1953 because that's after the atomic bomb. Why is it important that in 1953, after the atomic bomb, you have Watson and Crick finding their work? Well, because they used the equipment, the X-ray equipment that was being developed for the atomic physics. That equipment became available after 1945 for other use. And as the other uses were picking up, they realized that they could use X-rays to take pictures of crystals. and they realized that they can get molecular structure. So let's say, okay, if you can do X-ray crystallography and get the atomic structure of large order molecules, then the DNA is a large enough order molecule that you can put this in front of an X-ray machine and take an X-ray of it. You can get a picture of DNA, and that's exactly what they did. And they were able to see the first DNA molecule. But to get to this point, to get to the 1950, the textbooks leave out an enormous amount. Basically, I have a list that I'm going through now. I'm doing research on a list of 23 different physicists. This is all from 1900 to 1960. This is in the period that we have the growth from atomic physics down to nuclear physics to particle physics to quantum physics to superstring theory to quantum electrodynamics to a large extent a lot of the more advanced physics that are around today. The base work was done between 1900 and 1950. That's basically the atomic era. But the thing is that of the 23, the public is only aware of 3. And this is the first 3 that people are aware of. People might be aware of Max Planck. Max Planck is the work that sort of started all this inquiry into the atomic structure. Because before Max Planck, everyone thought that everything was already done, everything was already known. Max Planck came up and showed that there were a lot of unknowns still in physics. And this unknown stuff, this strange behavior, occurred when he started playing with light. And as they started playing with light, they started going down to the smaller and smaller levels. And this is actually what Einstein picked up. Einstein picked up Max Planck's work and developed his theory of special relativity. He developed 2 theories. He developed the special theory of relativity, and he also developed general relativity. Special relativity had to do with the structure of atoms. General relativity had to do with gravity. And it's from the general relativity, Einstein's work on general relativity. That's where you get black holes from. Black holes are created in general relativity. That's where you first start seeing the concept of a black hole. The only other scientist that people will sort of generally encounter in your general science courses is Niels Bohr. Niels Bohr is a physicist, and that's what you learn somewhat in school. And he gives us the basic structure of the atom. If you see an atom, and you've learned about the atom in junior high, that's when you start learning about the atom. You know there's a core, there's a nucleus, and around the nucleus there are atoms, there are electrons, there are electrons orbiting the nucleus. And this is what you find from Bohr. They call the Bohr model of the atom. And that's as far as it goes. They don't tell you anything more about Bohr. Bohr is, he's the one who gave us the Bohr model of the atom, the standard model of the atom. Every kid in junior high learns. If you go to a junior high science fair, and you see some kid has a model of the atom, that's the Bohr model of the atom. That's what he's been learning in school. What you're not going to see at the school and taught in any textbook is that Bohr was a Nazi scientist. He was a Nazi, and he was part of the Nazi atomic bomb team. That's right. There were 3 teams there were 3 atomic bomb teams. There was a German team, there was a British team, and there was an American team. If you know about the American team, the American atomic bomb, you know who was the head of the atomic bomb, doing the head work, you know about Robert Oppenheimer. That's Oppenheimer. That's if you've heard about the atomic bomb and have learned about, who's at the top. Who else might you know? You might know about or have heard of the name Enrico Fermi. There's a lab called Fermi Lab in the United States. Well, that's Enrico Fermi. You may have, if you've taken chemistry, you may have heard of Wolfgang Pauli. There's the one we all have heard about, but no one actually knows his name. That's Werner Karl Heisenberg. Right? They talk about the Heisenberg uncertainty. Well, that's Werner Karl Heisenberg. Ironically enough, he was another German scientist. He was another Nazi scientist. Then there's another, again, only if you've taken a certain amount of physics, you'll know this person. Again, we're getting further and further outside of common knowledge, is Paul Adrien Maurice Dirac. Dirac has several equations in quantum physics that are named after him. Then there is, if you go into particle physics, you'll know about something called Feynman diagrams. And anyone who is, heavily into physics and into quantum physics knows the name Richard Feynman. And he is another important scientist here. He worked on a theory called quantum electrodynamics and something else known as quantum field theory. And this is why you have the Feynman diagram. The Feynman diagram is how particles behave. It's a diagram showing the relationship of particles to their fields. And this is where it gets really complex, because in order to get into the work that these scientists have done, which I've basically named 9 scientists. The first 3, most people would have heard. Most people know about. I think the most common one is Einstein. The next one is Bohr. If you know about the atom, anyone who knows about the atom learned about Bohr. The one that's kind of further out is Max Planck, and then the rest that are you have to have high school and above for the for 4 to 9 for Enrico Fermi, Pauli, Heisenberg, Oppenheimer, Dirac. Well, okay, let's do it this way. For high school education, you should understand Fermi, Pauli, Heisenberg, and Oppenheimer. These could be commonly found inside of a high school textbook. You will not see them in high school text. You will not see Dirac or Feynman. Dirac and Feynman are the ones you run into your first and second year of university. This is when you first start running into these people. Also on the list, but this is, again, completely, this is not until you get further into this, right? I've now mentioned 9 scientists, 9 physicists. There are now still, 23, there are now another 14 scientists we talk about. The next 3 are very famous, and they're known well to scientists. If you're in atomic physics, you know these people, because there's a famous paper called the Alpha-Beta Gamow paper, and it's also known as the Alpha-Beta Gamow conjecture. If you watch some of the TV show Big Bang Theory, sometimes they mention this paper called the Alpha-Beta Gamow conjecture. That's 3 scientists, 3 physicists: Ralph Asher Alpher, Heinz Albrecht Bethe, and George Gamow. It's a W, but some people say Gamow, some people say Gamow. There are 2 pronunciations. You can take your choice. And these are the next 3 scientists that you kind of run into if you've been doing physics for a bit. This is the next 3 you run into, because they have a famous paper, and people start telling you about their paper. You hear conversations about their paper, about the Alpha-Beta Gamow, the Alpha-Beta Gamma conjecture. You hear about that. This guy says, well, when you go to try to find the paper, you find the paper, because it is a famous. You can actually Google it. Do the Alpha-Beta Gamma, and it has a B in Greek letters. Paper. Do that, and you'll find Ralph Asher Alpher, Hans Albrecht Bethe, and then you have George Gamow. The ones you don't see that are also important are Edward Teller, Leo Szilard, Eugene Paul Wagner, or Wagner, depending on how you pronounce it. Then there is Carl Friedrich von Weizsäcker. Some of the names are a little difficult to pronounce. Murray Gell-Mann, Arnold Johannes Wilhelm Sommerfeld. Then there's Julian Seymour Schwinger. Then there is Freeman John Dyson, Sir Rudolph Ernst, and I can't pronounce his last name, so I'm not even going to try, but he's English. Walter Heinrich Helter, right? And then there's Edwin Ernst Salpeter. And that's your 23 physicists that are key to the work that was done on atomic physics from 1900 to 1960. Is that of the 23, two are known generally. That's Bohr and Einstein. Some people in high school may have known about Planck, but that's also kind of a rarity. And the rest, again, fall off into unknowns. It depends on how far you get into physics. And so what happens is you see what was in the textbook, and you see now how much it's outside the textbook. That a large chunk of what actually happened in atomic physics, what was going on behind the scenes of society. And during this period from the 1900s to 1960s, what do you have here? Basically, you have the flappers. That's the 1930s of the flappers in the jazz music. You have 1950s to 1960s. That was your sock hop. That was your the beginning of rock and roll. 1960s were the hippies and the love age. 1970s was again it was the beginning of the computer age. This is when we had Apollo 7. It was even though the space age was officially the 1960s, the space age didn't really become part of the public viewing until 1970. That's when you really had the beginning of Star Trek. You had Lost in Space. A lot of space and science shows came out at the time. I remember as a kid on ABC, the morning cartoons, they had Rocket Ship 7 because the channel was number 7 on the dial. It was ABC, and they had Rocket Ship 7 with Commander Tom. And every Saturday morning, you'd get whatever you have, and you'd sit in front of the TV, and you'd watch Commander Tom blast off on Rocket Ship 7, and he'd take you to all these different cartoony places. And that's how you did your cartoons. And of course, every time there was a launch of the Apollo rocket, the Apollo missions, everyone turned their TV on and you watched the rocket launch of Apollo. Just the way everyone watched in the 1980s, everyone sort of 1980s into the 1990s, everyone watched the space shuttle. In the 1970s, you watched the Apollo missions. It was the age of the Apollo missions. And so what happens? You had a public view of science, and you had a researcher view of science. And this began back in 1930. And this is what we have to do: is we have to go back. We have to take a look at how society, which is primarily atheistic, it's secular society, grew up with these blinders on, not seeing what's going on underneath. And a large chunk of this, and I know if two people are watching this, and this is basically Bishop Moses and my dad, this is where you have to turn to now. You have to turn to two particular psychologists, and they're Sigmund Freud and his nephew, Edward Bernays. Sigmund Freud created the underlying philosophy that is at the base of today's psychoanalysis. Today's society is all based on psychology, on social engineering. Well, that's the base of the work. The base theory is Freud. The application of this base theory that produced what we call modern secular society, the consumer society, the visual society, if you will, was Edward Bernays. He's at the cornerstone. He's the fundamental. He is the building block that the modern secular society was built on. He was the advisor to Woodrow Wilson in the construction of the UN. And so what happens is that you have two different sciences competing for attention. And what happens, the military realized, and this is why Tesla's work disappeared. The military realized in the 1930s that they could use the work by Edward Bernays to create a dual society. A society of the seen, in other words, public society that the standard public would see, and a hidden society that only a select few of people could actually see this hidden society. And the hidden society was your atomic physics. It was anything that could be weaponized was hidden. And it was hidden in plain view. All you had to do is put up enough circuses, put up enough distractions, keep people entertained, you know, the Roman circuses, if you want to go back to that thing, and you could keep people's attentions away from what's actually going on. This is how you create conspiracy, because when people are distracted, you walk off with the real stuff. You know, it's the pickpocket in the crowd. You know, the crowd is focused on something else. You know, they got the dancing monkey, and while the dancing monkey is going on, that the organ grinder has a collection of people going around picking people's pockets. You know, he's not making his money off of donations from the public. He's picking people's pockets. And this sort of same analogy, applies to what happened with Edward Bernays' work and the military. They wanted to get people's eyes off of what was going on in the military, on possible military research, and the way to do that, you created enough spectacle so that people's attention was turned away, and while they were turned away, well, all of Tesla's work disappeared. Bases at Area 51 were set up that were top secret, and they began doing all this top secret research. And this is where you started seeing UFOs, you started seeing, having experiences with aliens, and all the different things came out of this. And the thing is, because these things are interrelated, we do have to talk about them because these are a consequence of what was going on when they were working on the atomic bomb. And that's why I say the title is appropriate, Atheism and the Atomic Bomb, is because there's an enormous amount to talk about here, particularly if you parallel it to what was going on in society at the time. So that's actually what we're going to do. We're going to spend 12 weeks, when I come back on August 11th, we're going to spend 12 weeks going into an introduction that will really take us into the meat. We're going to spend 1 week on each topic. We're going to do psychology 1 week. The second week is going to be psychiatry. Then we're going to do eugenics and genetics will be the third week. The fourth week will be Tesla and the war machine. Fifth week will be the atomic age and postmodernism. That's basically 1946, 1945 and 1946. That's the beginning of it. Then we go just not even 4 or 5 years later. We'll spend 2 weeks in there. We'll spend the sixth week will be nihilism and pragmatism. That's the 1950s. Also within the 1950s, we'll talk about, this will be week number 7, we'll be talking about the beatniks and sock hop. The sock hop. Week number 8 will be hippies in the space age. That's 1960s. Week number 8 will be dawn of the drug addict and the computer age. That's the 1970s. And the dawn of the drug addict is an overview from a research perspective of where the drug addict came from and the experiments on LSD. That was sort of the drug addict that you saw in the 1960s, in the 1970s on the street, was the end result of the experiments with LSD that began in the 1930s. That produces our week number 9. Is anarchy, crack, and the PC. That's the 1980s. That sort of sums up the 1980s. Week number 11 is going to be the social weapon and economic welfare. That's the 1990s. Week number 12 is going to be progressive fascism. That brings us into the new millennium. That brings us into 2000 and the current state that we're in now. So we have quite a bit to do here. There is a lot. As it, there isn't a fast way. There isn't a fast way to get out of this. One of the the commenter that I had talked about before. His name is what was his name? I gotta go back to my notes, see what his name is. His name was Jeremy H. Jeremy H. Felt that I was attacking his religion. He was an atheist. I'm assuming there, because he says he doesn't want to see people attacking atheism, and he wants to get to the good part, good stuff. Well, the thing is, this entire discussion we've had now, not once have we talked about religion. Not once. It's all been about physics and the consequence of what happens in physics. And he said, well, let's get to the good stuff. Well, if you're doing research, you can't fast forward to the good stuff. All these different parts have their degree of importance. And why am I saying this stuff for 12 weeks on this introduction? Because we're going to spend an entire year going further into it. And it's not until next year, next August, we're going to get into the details. And the details, unfortunately, this is where the details are such that it causes comas. And this is the heavy mathematics. This is the calculus. This isn't simple calculus. This is advanced calculus. This is vector calculus, field calculus, path integrals, various different complexities trying to deal with calculus on a surface, calculus on a sphere, calculus in a solid, calculus in two planes, in a plane, I should say. And I'm not talking about an airplane. I'm talking about, if you know what a graph is, a two-dimensional graph. A graph of 2 dimensions is a plane. The single line is a linear existence. So when anyone talks about linear, they're talking about straight lines. Then you have your curves. You have your parabolic curves. You have your polynomials. I mean, we're getting into a lot. This is where, if you want to get into what happened, where the failures were, you want to see the failures in physics that sort of push things along. Well, it's in the mathematics. And at the end of it, we'll spend at least 3 years in the mathematics. And every time we go through the mathematics and we go through these equations, I'll be saying to you, well, you know what? At the end of the day, these equations, no matter how much time you spend on them, are simply approximations. And as I proved this, I demonstrated this, and this is why I was sort of looking around at different things. That you have this with dark energy and dark matter. You have this with the Heisenberg uncertainty principle down on the molecular level. We've seen this again where you had to fit the equations to meet the data for the Higgs boson. We've seen this when you're building an aircraft. When Boeing started building the Dreamliner inside the computer system, they did it all within computer simulation. They tried to model the whole thing. It didn't work. Their equations were not exact. They thought they were exact. They thought they knew everything. And this is where I said the human being, you have to, as a physicist, you're aware of this. When you're saying, and you're doing this type of physics, and you're aware that you're never dealing with the absolute. Sometimes you'll say things, understanding that you're not talking about the absolute, but other people will assume the absolute. So what I'm saying is that when I know something or I understand something, I understand within a degree, within the limit. And the same thing here when they're working on the equations for engineering. They were supposed to have it absolutely, but they didn't. They had it in the limit. But they didn't understand that this was the limit. The things that they considered to be insignificant. And so we're not dealing with that right now. So we can sort of chop this off. This view isn't significant to us. We'll simply deal with what's in front of us, the things we view as significant. And that's how they fit the Higgs boson. But the problem is, a lot of your answers as to what's actually going on and where your lack of understanding is not in what you know, it's in what you don't know. And so for me as a physicist, I'm not interested in what you got right in your equations. I want to know what you got wrong. Where is your theory flawed? Do you have data that doesn't fit what your theory is supposed to say? Because if you do, that's telling me something else. And I want to see what that something else might be. And not that I know what it is, but I want to see what it might be. And the thing is, this is why in some cases, when a scientist comes out with a discovery, you gotta, in the back of your mind as a researcher, you go, well, okay, is it a discovery or is it something else? In physics, and in astronomy, you often have appearances. Things will appear to be something, but it's not until maybe 5-6 years down the road that you've got enough research put together on this thing that you realize that it's something else, or could be something else. So this is kind of the thing we're dealing with. We're talking about atheism here. You're talking about, oh, you're attacking atheism. You're being religious. Well, no. I said I have not once have I really talked about religion in here. This is about physics. This is a question of physics and how physics and what happened in the atomic bomb and the development. And let me. 2 out of the 23 scientists are well known to the public. The rest of the 21 scientists are barely known to society. Barely known. And they're really not in any text. You're not going to be able to find them in the textbook. Planck maybe, Fermi maybe, but you're not going to find that much. And as a matter of fact, the stuff when I've done a general search on Planck, is not what the write-up on Planck is not what you see inside of his research papers. In other words, the matter of fact, the write-up on that I saw on the internet, even from some universities, from their undergraduate sites, they're horrible. They're pitiful. There's a lot of wrong information in them. Anyways, it's now 11 o'clock. It's time to move on to our next platform, to YouNow. We're going to continue over there. So if you would like this discussion, you want to hear more of this discussion, the link is up on the chat. I've got it up in the chat. It's going to be YouNow. That's younow.com/cyborgalpha. We're going there. We'll be there in about 5 minutes. We'll do another hour on YouNow, and then from there we'll go over to Twitcasting. Twitcasting is us.twitcasting.tv/cyborg_alpha. And we'll be there from basically after YouNow. We'll be there, and on Twitcasting, that's where we'll be doing our Q&A. We'll have a bit of discussion. Usually we have about 15 people joining us on Twitcasting, so there's a fair good group. But I need to to sort of make you aware that our audience ranges in age from 14. Our audience is as young as 14 years old. Please be careful on what in the language that you use. I don't care about the language myself. You can use whatever you want to use. But there are kids as young as 14. So this is something you need to be aware of when you're typing. You don't have to make your questions easy. It's not about being easy. I'm talking about if someone wants to make a comment, just make sure your comments are appropriate. But I understand sometimes that this may not always be the case in terms of the way you can phrase things or the way you know how to phrase things. Anyways, I will see you in about 5-10 minutes over on YouNow. Watch for that broadcast coming up. And if you want to follow these broadcasts, the best place to follow me on is Twitter.